Hey friends, welcome to my channel, and this is the next episode of the name reaction. And in this video I will be talking about two name reactions, Appel reaction and the Corey-Fuchs reaction. I have chosen these particular two reactions because their mechanisms are apparently similar, and you can see the reagents used for these two reactions are also similar. The tetrahalomethane and triphenyl phosphine, this is common for both of the reaction, and when I will discuss the mechanism you will see the other similarities. And also these two reactions are very important because there are several reactions where these two reactions are one of the states, and these reactions came in CSIR exam a lot of times. So if you don't have the knowledge of what are the consequences of this reaction, then you cannot do that answer, but if you know it, it is very easy to do. So that's why I have chosen this one. So now let us talk about these reactions. So you can see in the Appel's reaction what is happening. Alcohol is converted to a alkyl halide, and in this case if the alcohol is a secondary alcohol and the center is a stereo center, then you can see the inversion of configuration occurs. That is, it is a backside attack, and it implies that it is basically a SN2 reaction. Whereas for the Corey-Fuchs reaction, aldehyde is converted to alkyne. So now let us see in detail what are the mechanisms involved in these particular reactions. So I will first talk about the Appel's reaction. So in Appel's reaction, if you look at the reagents used, it is basically a tetrahalomethane, that may be a tetrabromomethane or a tetrachloromethane. So let us take in general a tetrahalomethane. So it is basically X, 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 and you have triphenyl phosphine and you have your alcohol. Okay, so just by looking at these three reagents, what should come in your mind is that something will attack on something. Now what will attack on what? So you can see here this triphenyl phosphine and this alcohol both are nucleophilic because both have lone pair, but of course triphenyl phosphine will be much more nucleophilic than your alcohol, because the 0.1 oxygen is more electronegative than phosphorus, and also due to the presence of these three phenyl groups on phosphorus, its nucleophilicity will further increase. So if a nucleophilic attack has to occur, it will obviously first occur by the triphenyl phosphine. Now so we find our nucleophile, that this triphenyl phosphine is our nucleophile. Now we have to find what will be our electrophile. So in this case you can see this is actually electrophile. You can see these two are nucleophile, so obviously this will be the electrophile, but you have to find out the electrophilic center at this particular molecule. Now normally if you have an alkyl halide, what happens, let's say you have methyl halide or methyl chloride, any alkyl halide. So in that case this methyl carbon is the electrophilic center, and in this case also you can see the same type of carbon is there. This is the methyl carbon, so you can think that it is electrophilic center, and indeed it is electrophilic center, but a non-nucleophile can directly attack on it because it is surrounded by 4 halogen atoms, and the size of this molecule is not so large that the nucleophile will overcome these halogen groups and it will attack on the carbon. So although this is a electrophilic center, but these nucleophiles cannot attack on the carbon, so it has to find some other electrophilic center. Now if you just think about more deeply, that is what is the origin of the electrophilicity of this carbon. So basically the origin of the electrophilicity carbon is due to the presence of this sigma star orbital, this CX sigma star orbital. This is the center of the electrophilic carbon. Now if the sigma star has a coefficient on carbon, that should also have a coefficient on the halogen atom. So basically what I am trying to say is that the electrophilic center or the electrophile here is the sigma star orbital, which has both coefficient on the carbon as well as on the halogen. Now as the approach of nucleophile on the carbon is hindered, so it will find some another electrophilic center, and that is basically the sigma star coefficient which is on the halogen atom. So your nucleophile will attack on the halogen and it will give you this. Okay, so here you will have a positive charge and here you will have CX3 minus. Okay, now you can see by this step you generate electrophilic phosphorus center. So previously this phosphorus was not electrophilic, but in this case you can see a positive charge comes on phosphorus, and now this which was previously a nucleophile, it now becomes an electrophile due to the presence of this positive charge. Now the other nucleophile present in your reaction medium is this alcohol. So the alcohol will then attack on this phosphorus. So if we take our original molecule, what we will get is, we will get this R dash, and here you will have O PPH3 plus. So basically what happens here, you have PPH3 plus X, so this OH will attack here and it will go, so you will get this. Now in the next step what happens is that you can see this X minus is removing in this step. So X minus is removing in this step. So this X minus, although it is not a very good nucleophile, but still it can act as a nucleophile, and in this case you can see this is a nucleophile, and other nucleophile present is CX3 minus, but you can see CX3 minus is very bulky, so its nucleophilicity will be reduced by its bulkiness, and that's why the X minus will serve as a better nucleophile, and this X minus now can attack from here, and it will this bond will go here, and you will get this product. Okay, so as a byproduct you will get triphenyl phosphine oxide, and this is the same byproduct as per Wittig reaction, and you know this PO double bond strain that drives this reaction to the right hand side. So this is basically the reaction mechanism of the Appel's reaction, and also this salt which is formed P53 plus X minus, and with that P53 plus X, and at the same time actually you have this CX3 minus. This was formed in the first step, and this is called the Appel's salt. So in some cases the ready-made Appel salt is added with your alcohol, and you get this alkyl halide product. So this is the mechanism of the Appel's reaction. Now there is no complicated thing. If you get any example, you can easily recognize that these are the reagents, and we have alcohol in our or OH group in our molecule, so it will definitely do the Appel's reaction. So there is no complicated thing, so I am not discussing more examples of this. So let us move on to our Corey-Fuchs reaction. I already discussed it, but I want to discuss it again because it has similarity with the Appel's reaction. So in the Corey-Fuchs reaction, what happens is you have your aldehyde and the same reagent, let's say CBr4, and your triphenyl phosphine in the first step. In the second step, you are given BULI. So you will get this alkyne. Now what is the mechanism? So the first step is same. First step, this triphenyl phosphine will attack on the bromine, and you will have this you will have this Br and plus, and with that you will have CBr3 minus, like the same as the previous case. Now in the previous case what happened was that your alcohol OH group, ROH group, this alcohol make attack on this phosphorus, but you can see in this case you don't have alcohol, you have ketone. Now ketone is less nucleophilic than alcohol due to the two reasons. One is that you can see its hybridization. If you consider this is sp2 hybridized, and in your alcohol it is basically sp3 hybridized, and you know if hybridization S character increases, its electronegativity will increase, and that's for this increase of the electronegativity, the ease of donation of the electron density or the tendency for attack on electrophilic center will decrease. So that's why it will be less electrophilic. And the other reason is that after formation of the bond, that means after attack, you can see for alcohol, if it attacks on any electrophile, its positive charge can be neutralized by removal of this proton. But in this case, you can see if it makes an attack on the electrophile, it will persist the positive charge of the oxygen. So these two reasons makes any carbonyl compound less nucleophilic than an alcohol. So in this case, what happens? Instead of this carbonyl compound, this CBr3 will attack on the phosphorus, and it will form this P53 plus, and here you will have Br. Now in the next step, what can happen? this Br minus which is removed in this step, this Br minus can come and it can attack on this bromine and it will form this ylide. Okay, so this is basically the phosphorus ylide, and you can represent the same ylide like this way also. Here you have minus and 2 Br. Okay, so this is a phosphorus ylide. Now you have a ylide and a carbonyl compound in your reaction medium, and you know, if you have a phosphorus ylide and a carbonyl compound in your medium, it will do a very famous reaction that is called the Wittig reaction. So Wittig reaction occurs between these two partners. So here you have R and here you have PPH3, Br, you have Br. So it will do the Wittig reaction and you will have this. So here you will have bromine, you will have R. So this Wittig reaction occurs and this oxyphosphatane collapses to give you first this alkene. Okay, so you get your alkene. Now in the next step what happens is that you have so in the first step you will get this alkene. Now in the second step you are employing the butyl lithium. So what butyl lithium do? So butyl lithium will do this elimination reaction. So it will take this hydrogen and it will go like this. So by this elimination reaction you will get this product. So this alkyne you will get, but you have a bromine here. Now again you have butyl lithium, and this butyl anion can attack on this bromine to give you this this anion, alkylate anion. So you will get this anion. Then after that you will do workup with your acid medium. So when you will do workup with your acid medium H3O plus, so you will basically get this alkyne. So this is how your aldehyde gives this alkyne. So this is the full mechanism of the Corey-Fuchs reaction. Now it's a very important reaction, and definitely you should practice it several times to grasp the actual mechanism, and you should be able to write it by your own.